My name is Flavio. I'm from the University of Algarve in Portugal. Although at this point, at this moment, I'm in the other side of the Atlantic. I'm in the Dominican Republic, so it's morning here. And I'm also in a place with a bit of noise and some internet issues. So I hope it doesn't become a problem. I hope you don't hear too much noise, and also I hope the internet keeps stable, at least during this session. Yeah. So I guess we can start. Still don't know if this session is 2 hours or 1.5 hour. I was asking Audrey about that, so I will have the answer in a minute. Anyway, does anyone of you know if it will be 1 hour or 1.5 hour or 2 hours?
It's varied. It's been between 1.5 to 2 hours, depending on the lecture. Last time it was 1.5. The time before it was 2.
It was 2 hours. The last one, was it?
The last one was 1.5. The one before that was 2.
Okay. And you don't have a plan? You
No.
didn't receive a plan with the time?
No.
So, okay, I will assume around, I would say 1.5 hour, and then we can maybe discuss a bit in the end. I also asked Audrey, and she will for sure answer in a few minutes. Anyway, so I'm sharing my presentation. Okay, I hope you can see it. I will also try to maximize my screen.
Hi, Flavio, we can see your screen.
Yeah, okay. Yeah, I was just hiding the controls to have the full screen for me also. Okay, so this session is about operational, but basically about modeling and focused on operational modeling. You will see in a minute what does it mean, or what operational in this context means. And it's a very brief introduction. Those of you that will attend the BIP course, the in situ course, the presential part of the course, you will have another session. Oh, Audrey is answering me that it is up to me. Okay, so it's even better. I will go in my pace, in our pace, and whatever it happens between 1.5 and 2 hours. So I was saying, those of you that will attend the presential part of the course will also have a hands-on session about modeling, and in that case it will be kind of a workshop, so you will actually learn how to use a model with a graphical interface to run some very simple but complete example of an estuary. In that case, I'm preparing an estuary because it's something that runs fast and it has some exciting results. So in this part, it's a more introductorial part of modeling and focused on operational modeling. So any questions after this presentation, you can address it to me. You have my mail here. You will also have this presentation, so you can address it directly to me. Okay, so this is a short summary of what we are going to have today. So starting by the question, what is a model? And also discussing a bit about the transport of a property and the two methods of describing the transport of a property. Then discretization in space and time, two very important concepts in modeling. And then model limitations, the initial and boundary conditions of this kind of models. We will also discuss a process called downscaling and the different types of models that exist. And then we will discuss what an operational modeling cycle is. So what is an operational model? And we will also discuss concepts of data assimilation, analysis, reanalysis. Those are the names that you have probably already heard, but maybe you don't have a clear mathematical view or statistical view about what they mean. And finally, talking a bit about model calibration and model validation. So starting with the question, what is a model? And now I want you to be interactive. I want you to switch on your microphones and tell me, what do you see here? What do you see? What is this?
An apple?
An apple, yeah. Anyone have a different idea, a different opinion? Or is it really an apple?
Drawing of an apple.
Hello? Yeah? Anyone?
Of an apple.
Sorry?
Oh.
Please a bit louder.
Can you hear me now?
Yeah. Now, perfect.
Okay, it's a drawing of an apple. Right?
A drawing of an apple. Okay, is it really a drawing?
Yes, I think so. No?
Oh, okay. So, or is it a picture, a photograph? Okay, and this one, this is clearly a drawing of an apple, right? It's a painting of an apple. Okay, it shows different things, right? It doesn't show that much of the reality, but it gives some movement, some energy, some feeling, let's say, some emotion of the apple, right? Some impression. It's an impressionist, so it gives some impression of the apple. This one is also a drawing, but it's a pencil drawing of an apple. So this is, okay, this is, some of you say it's a drawing of an apple. In fact, it is. It is a painting, a hyper-realistic painting of an apple, okay? So all these paintings or representations of apples, they are not the real apple, okay? So they lack a lot of properties the real apple has. Like they don't have scent, okay? They don't have juice, they don't have seeds. There are a lot of attributes in the reality, in the real world, which are lacking in these different representations of the apples, okay? So basically, these are models of apples, okay? So a model, it's nothing more than an approximate representation of the reality, okay? So like this example, the mathematical models that we are going to use, so they are approximate representations of the reality. They don't have all the properties, all the behaviors that we see in the real world, okay? So due to very different reasons, due to computational power, we don't have enough computational power, but even more basic than that is because sometimes we don't really know all the details about the reality, okay? Because we don't have enough measurements, because we don't know the processes. For example, in case of biological processes. We don't know all the details, so we create an approximate model of the processes, but we still don't know all the processes. In a physical case, the equations are quite simple and we already know them. But in that case, the problem is they are difficult to solve, okay? But independently of the reason, the models will always be an approximate representation of the reality. So basically, it means that the models are never right. They are always a bit wrong, a bit different from the reality. So our job is to keep that difference as small as possible, taking into account our objectives and our computational power. But we must always remember they are approximations of the reality. Okay, so this is a very important concept for you to keep. So and you should know what are the assumptions in a model so that you don't start searching for things that the model should not show. The same way that you know the assumptions of this drawing. You know there is no scent here, there is no juice, there is no seeds. So there is no point on searching for, scratching the painting, looking for the seeds. There are no seeds. We know this model of the apple doesn't have seeds. So the same in a mathematical model. For example, if you decide to simulate an estuary with a 2D model, so basically you don't have differences in velocity from the surface to the bottom of the estuary. So there is no sense searching for stratification or a salt edge in the estuary using that kind of model, because the model don't show it. It's a 2D model, cannot show it, okay? So we must always have in mind the approximations that we assumed in order to know if that model is adequate for what we are studying and if we should be looking and searching for something that it makes sense or not in that kind of model. Okay, so so again, a model is a representation of the reality, and a more formal way of discussing it is saying that a model is, in our case, our mathematical models, it's an operator that operates among the input data, okay, and it transforms, so it's a set of operations that transforms the input data into output results, okay? So this is a very schematic way of describing a model. And the model can be used at least for 3 different objectives. So the most logic and simple way of using a model is if you know the model formulation, so the operator, and you know the input values, you use the model to obtain the output values. So yeah, this is the usual way of using a model. It's called simulation. It's useful for predictions and also sometimes to understand the system. If you run the model with different parameters of different input data, you start understanding better the behavior of the system. Okay, so this is one use of a model. But we can also use a model in a different way. So we can have the input data and the output data. Okay, if we have at the same time the input data and the output data, we can define the model, okay? This is called system identification. In terms of our algebraic models, the kind of models that I will be showing today, they are algebraic models. They are based on fixed equations. We start by knowing the equations. that connects the inputs to the outputs. But even though this can be used to obtain parameters for those equations, okay? When we have a calibration process, we are looking at parameters. So we have input data, different output data, and we are defining some parameters here. But if you start talking about artificial intelligence and data-driven models, this is one of the most important steps on creating a data-driven model, because you have input data and output data of the test samples, okay? So you have a set, which is the training set, and you must find, in that case, you are really defining the model. So the equations are not fixed at the beginning, so there are generic equations with lots of parameters, and you are defining the equations at this phase, okay? So this is system identification. Sometimes you also use a model in a different way. Sometimes you already know the output and you know the model formulation. And what you are trying to figure out is what is the input that produces that output that you have, okay? This is called the inverse model. So asking what's the input that produces this output. This is very useful in management, in decision making, because usually in decision making, you know what you want for that system. For example, you have a threshold of pollution for that system. You know, this system cannot have a higher concentration of pollutant, cannot be higher than this. So the question for the decision makers is how much is, what's the maximum input discharges so that we don't surpass the specified output, okay? So this is done with the inverse model. Sometimes we can really mathematically inverse the problem, and sometimes we do it by running scenarios. So it depends. There are many different ways of doing this. Oh, by the way, you can interrupt me whenever you want, whenever you have any question, okay? Just ask me, okay? Don't wait to the end to ask me questions. Yeah? Okay? Okay, so again, what's a model? A simplification of the reality, right? Okay, like these guys over here, they are models, right? They are models, so they are abstracted versions of the reality. They are not like this, you know, when they wake up in the morning and look at the mirror, they are not like this. But unlike this, so basically we are talking about mathematical models, but there is some difference between these two kinds of models, because unlike these models, the mathematical models, they improve with age, okay? These guys here, no. I can prove you these guys don't improve with age, you see? They really don't improve with age. This is just a joke, but to tell you that whenever you hear about a new model, it's a brand new model, suspect of that, okay? So it must pass the proof of age, because it must be used many, many times for the errors to be detected, for the parameters and the way the equations are solved to be improved, okay? So usually old models are better than new models. What most times happen is that the old model gets new improvements, okay? And that's even better. So we improve the model by changing some way of solving the equations, or changing some formulation for some term or some parameter in the equations. And that's great, that's great. But saying that a new model that was written from scratch is good, I don't trust it, okay? So most of the models that you will be using in this kind of ocean models and coastal models, their origin comes from the 70s, 60s, 70s, maybe 80s. Okay, so the thing is, they change language, they change the formulation of the equations, they change many things from those times, but the essence of the model is still, the roots are still there. Anyway, so I would like to talk a bit about the transport of a property, which is something that we always see in the textbooks with a lot of interesting equations, to say something, but probably I had that difficulty when I was studying, and you probably have the same difficulty, which is it's difficult to grasp. So you see the equation, you understand it from the mathematical point of view, but it's difficult to grasp the meaning of each of the terms of the equations, okay? Specifically the transport terms. So I'm using this analogy of a balloon. So imagine a person which is seated inside a balloon with a, for example, with a thermometer, okay, with a sensor. Let's think about temperature, which is something easy to think about. Imagine the guy have a thermometer in the balloon. So, and imagine that the environment has a derivative of the temperature as a function of time. So basically the temperature is increasing or decreasing in time, okay? So this is the change in the environment outside the balloon, okay? My question is, how much is the derivative the guy is measuring inside the balloon? So anyone want to say, to have an opinion on that? How much? Is it the same as this? Is it higher, lower? Does it have any other influence? What do you think? Anyone? Any question? No? Okay, so I can tell you that obviously the balloon is there in the middle of the environment. So the change in temperature the guy measures is exactly the same as the environmental change in temperature. Okay, so this is the simplest case. Now imagine that the temperature is not changing in time. The environment is not changing in time, but it has a space gradient. Okay, imagine the balloon is here, but the temperature is increasing with distance. Okay, so if the balloon is stopped, the change the guy measures in the balloon is zero because there is no change in time. But if the balloon has a velocity and it moves from places with lower temperature to places with higher temperature, obviously the temperature the guy measures in the balloon will change, okay? And how much does it change? Anyone want to have an opinion on this? No? I would like you to be more responsive. Any idea? Okay, so it will depend on the change the guy in the balloon measures depends on the gradient, the spatial gradient. But it also depends on the velocity of the balloon, okay? For a certain gradient, sorry, this one, a certain gradient in space, if the balloon travels slow, the change will be slow. If the balloon travels fast, the change will be fast. So the guy in the balloon, what he measures is this, the velocity of the balloon times the gradient in space, okay? So let's think about the third situation. where you have an environment with a temperature that changes in time, but also has a spatial gradient. And the balloon again is moving with a certain velocity, and the temperature the guy measures in the balloon will be composed by two terms, the two terms that we saw before. One is the temporal variation due to the change of the environment in time. And the other one is due to the movement of the balloon, and it's called the advective variation, okay? So basically, these are two ways of representing the same process, the change of the temperature in the environment, okay? This way is a perspective. The way of the balloon is a perspective of a measurement moving in the space, okay? This is called the Lagrangian perspective. This way of describing the same process, the change of temperature, is based on someone like us that are fixed in space and looking of what is happening, but not moving with the flow. So this is called the Eulerian perspective, okay? So these two equations, they are saying exactly the same, but in two different perspectives, okay? And this is quite important to understand when we formulate the equations of the processes in a fluid, okay? Because in a fluid, we can think about a mass, a portion of fluid moving along the environment, and then we will have the Lagrangian approach, or we can think about being outside the fluid and looking at the fluid in a certain piece of space. And in that case, we have the Eulerian approach, you see? And they are absolutely equivalent. This is quite different from, for example, if the property is not temperature, but it's momentum, for example, okay? So if you remember, I will now move a bit. If you remember, the Newton law is force equals mass times the derivative of velocity. Okay, we call it acceleration, but acceleration is the derivative of the velocity in time, okay? So this is very easy, and we, all of you have done it in the high school using a solid. So in a solid, there is no question about this term. So all the pieces of this solid, they move with the same velocity, right? So the derivative of the velocity is easy to compute, okay? It's very, very easy. But in a fluid, it's not like that. Each particle is moving in a different way, okay? So usually, instead of using this Lagrangian approach, so when you think about a solid, it's the Lagrangian approach, is a piece that is moving. Instead of using the Lagrangian approach, what we use is the Eulerian approach. So we have a fixed portion of space, and instead of computing it as in physics, in normal physics, we compute it in these two terms, you see, based on a certain part of the space. And you will see that in the future, that this part of the space is a computational cell in our model, okay? So our model will have computational cells, and this piece of the space is a computational cell. So whenever you see these two terms, so the derivative in time, so the temporal variation, and the advective variation, you know this is equivalent to a movement of a Lagrangian portion of fluid, okay? Okay, so in terms of a fluid, the Newton's law is like this. We must remember that both the forces, the masses also, and the densities, and the accelerations are function of place, of the position in space, and also a function of time, okay? So these are field equations. So they are used as matrices, and they are field equations, okay? And this is the Newton's law for a fluid. So the forces are the different forces in the ocean, and the acceleration has the two terms that if you use the Eulerian approach, have the two terms that I told you, okay? So these are the equations. In fluids, the Newton's law is called the Navier-Stokes equations, okay? So basically, if you look at this, in this case, this is the two horizontal directions, 1 and 2, and you can see here the derivative, the temporal variation of the velocity, and the Eulerian variation of the velocity. If this u is outside, you have a nu multiplied by the derivative of the property. But in this case, the property is u itself, okay? And all these are forces, okay? So I don't think I have, no, I don't. So, but I can tell you these forces, what they are. You have heard these names almost for sure. So this is the Coriolis force. This is the barotropic force due to the water surface height. This is the barotropic force due to atmospheric pressure. This is the baroclinic force. So it's an integral in the vertical of the horizontal derivative of the density. And this is the diffusion. Okay, the diffusion is also a force because diffusion is stress. So it's also a force. Okay, so these are the Navier-Stokes equations. So in this case, when we talk about hydrodynamics, we know exactly the equations. We know them completely. The thing is, they are so complex to solve that nobody knows how to solve them analytically. Okay, there is still no way of solving it analytically. In fact, the Clay Mathematics Institute, it's an institute, an American Institute of Mathematics, and they in the year 2000 they created, or they identified 8 challenges, and they create these 8 Millennium Prize problems. Each prize is 1 million euros, okay? And one of the problems, so those are mathematical challenges of the century. One of the problems is, well, it's not really to solve the equations, not even to solve the equations. They just want someone to be able to prove the equation of the solution of these equations exists and is continuous, is smooth, okay? If you prove that, you will get 1 million euros, $1 million. But unfortunately, it's not that easy, and nobody managed to solve it until now. Yeah, because it has to do with turbulence and chaos, and so it's not that easy. So just to tell you, these equations are not solvable analytically, okay? So we need to use simplifications. We need to use models of these equations and solve them using what we have as a computational power, which are the computers, okay? So basically what we do is we transform these equations into a different kind of equations, okay? Using a numerical model, we change these partial derivative equations into algebraic equations, millions of them, okay? This process is called discretization. And then when we have these millions of linear equations, we can use the computers to solve them, okay? There are a lot of them, but the computers are also very, very fast solving them. So that's how we approximate the solution of the Navier-Stokes equations, okay? So this is about modeling. To do that, we need to do some simplifications, okay? The first simplification is simplify the space, okay? It's not creating a grid, okay? it looks like you are creating a grid in our space, but it's not that. Discretization is a bit more deep than that. We are not drawing a grid over our space. We are discretizing the space, which means that the space is not our normal space. In the model, the space itself is discrete, you see? There is no continuous changing from one point to the other. There is no continuity in the space, okay? The space is discrete. You understand what I'm saying, right? It's different from having a continuous space like our normal space and draw some lines over it, but it's continuous anyway. And the model space is not continuous. There are just that discrete points, you see? There is nothing in between those discrete points. Okay, this is the spatial discretization. And there are many ways of doing it, depending on our objectives and the type of model that we are using. It can be geographic Cartesian, okay? It can be Cartesian, orthogonal Cartesian. It can be curvilinear orthogonal. It can be triangular and structured. By the way, all the former are structured. These are all structured because each cell in the grid can be identified by indices. Okay, so we know we have an index I and J and K, and with those numbers we know exactly which cell we are talking about. So it's easy to identify, more important than that, to identify the neighbors of that cell, okay? If we know I plus 1 is the neighbor on the right, I minus 1 is the neighbor on the left. And that only happens in structured grids. Like this one, the curvilinear is also structured because although it's curvilinear, we can assign an I and a J to the indices. Okay, in the triangular grid or other types of grids with different shapes, they are unstructured. So it means there is no, so the cell 32, the neighbors are not 33 and 30. So it's impossible to organize that way. So we always need to know the numbers of the neighbors, and it causes a lot of difficulty in the computation. But on the other hand, you see what they can do with this kind of grids. You see, here, if you try to decrease the size of the cell, so to increase the resolution, it will increase the resolution in other places. So the places are dependent on each other in terms of resolution. And here, no, you can increase the resolution here and increase here, decrease there, and it's totally independent. So it's a very good property of it. Unfortunately, these grids, these triangular grids, are not good when you have flow, when you have the advective term. So they are very, very good for other purposes, but when you have flows, they are not very efficient. That's why most of the models that you will find, they will use structured grids, orthogonal structured grids. Some models also use this, but most of them use curvilinear grids. And also in the vertical, you can discretize in the vertical using different methods of discretizing. Okay, so this is the space discretization. But we also need to discretize in time, okay? You can ask me questions again. You are very quiet. I don't like to give classes like this. I want you to ask and to be active because it promotes. So probably one of you have one question and it's the same question other people have. So please interrupt me, yeah? Well, anyway. So discretizing the time. It's a process similar to what I said to space. the time is no longer continuous in our model, okay? It's different from setting some time instance in a continuous time. It's not that. The time is not continuous anymore. In our model space, let's say, space-time domain, in our model domain, the time is not continuous. We just have specific instance of time, and there is nothing in between. You see, there is no sense talking about some instant between two time steps. Okay, so the time is also discrete, and we discretize the equations in space and also discretize the equations in time. Okay, and in terms of time, the equations or the methods can be explicit. So probably you will have already heard about these names. Explicit. When it's explicit, what it means is that, so basically we are always computing. We are in time zero, and then we compute the values of all the variables in all the grid points in time one. And then when we have it in time one, we go one step further and we compute all the properties in time two, and then in time three, and in time four, and so on. Okay? If the method is explicit, it means that whenever you are computing a value in a cell in the new time, you will use the values of the cells of the neighbors in the old time. Okay? And because the old time is already known, all the variables are known in the old time, so this is explicit. You can compute it even by hand. In former days, the computers were humans. So they used to put a room full of people with a pencil computing numbers. So we can compute it explicitly, knowing the numbers of the neighbors. Okay? So this is an explicit method. And this is nice because we already know everything, but we are not doing the right thing. So because, you know, this is the model, but the initial equations, they are instantaneous. So they are time-space equations, and they should be solved instantaneously, not using the values of the old time, okay? So we are committing an error here. And the error will be big if the difference between time e and time I plus 1 is big. But if the difference between time I and time I plus 1 is small, the error is not that big, so we are not committing a big error, okay? So basically in explicit methods, to be safe, we have very, very small time steps, okay? Ti and Ti plus 1 will be very close, which means that the model will do a lot of iterations. So the computations are higher. So we need more computations, you see, because we need to keep the time step small. But the computations are very easy to do. So they are just so very easy computations to do. So basically we have many time steps with very fast computations, okay? But what we should really be doing would be the implicit method, would be to compute the new values based on the neighbors in the new time step, okay? So, but this is difficult to do because this point depends on the neighbor in the same time step, and the neighbor depends on this point. So it's kind of a connected ring. And it, at the first sight, it looks like it's impossible to do it because this cell depends on the other cell and the other cell depends on this cell. So how do I do this? But we can do it. This is what a system of equations do, right? When you write system of equations, all the variables depend on each other, and we solve all the variables at the same time, simultaneously, okay? So it's a simultaneous system of equations. it takes more time for the computer to solve this. You remember from your bachelor that there are those methods, the triangulation and the reduction. And so those are iterative methods that are used to solve the equations, right? So, but it takes time. It's much more costly in computational terms than this explicit method. On the other hand, the neighbors don't need to be close in time. So Ti and Ti plus 1 may be large, and even though we don't have problems. So basically, the two situations is either to have many iterations of fast computations, or a smaller number of iterations, but with longer computations of solving systems of equations, okay? And you may ask, which of these is more efficient in terms of time? In fact, none of them. Nowadays, almost all the models are semi-implicit. It means that they are implicit in a certain direction and explicit in the other direction, okay? And this may seem a bit strange and not logic.
We have
Yeah,
a
yeah.
question, Flavio,
Yeah, sure.
from Fernando. So we need something like an initial condition, he's asking.
Initial condition, I will go to that. Yeah, all these equations that we are using are boundary and initial conditions. Exactly. So in this case, the initial condition must exist. When we compute time 1, we must know all the neighbors in time 0. Yeah, exactly. That's why this is an initial condition problem. I don't know if I answer your question. Yeah.
Yes.
Okay, great. But I will talk a bit more about initial conditions later. Okay, so I was saying that the most efficient way, and that's why most of the models nowadays, there are still a few that are explicit, but most of the models are semi-implicit. Because in this case, it may not seem very logic, because in one direction, we use the neighbors in the old time step. For example, east-west, we use in the old time step, but north-south, we use in the new time step, okay? And because at least some of them are used in the new time step, we still need to solve a system of equations. The thing is that if we organize well our system of equations, instead of getting a system matrix that is sparse, you remember that, right, from the bachelor, you get a system matrix that is tri-diagonal, okay? They just have numbers in the diagonal and in the adjacent diagonals. And when it happens, the way of solving the system of equations is very fast. It's almost as fast as an explicit method. And even though we are using a method that is kind of implicit, it's not completely implicit, but it's kind of implicit. So basically what I'm saying is that we can increase a bit this delta t between Ti and Ti plus 1. We can increase it without a computational effort that is too much. So that's why we use it. But if we consider always the east-west explicit and the north-south implicit, the solution would start to get skewed, you see? So what we do is, in the next iteration, we change. We use the east-west implicit and the north-south explicit. And we are always changing the direction that is implicit and the direction that is explicit, okay? So that's why these methods are called ADI. ADI means alternate direction implicit, okay? So, and these are the most common methods used in this kind of models. So I'm now focused on ocean and coastal models, hydrodynamic models, okay? So, if there is no question, I'm changing a bit the subject. Is there any other question?
Doesn't look like it.
Okay, okay. So, as I said, models are approximations of reality, and they have a lot of limitations, errors and limitations. So one of the limitations I was telling you, I'm returning again to this slide, is that if we are using an explicit method or a semi-implicit method, the distance between ti and ti plus 1 cannot be that large, okay? So the delta t cannot be that large. Obviously, we are always trying to increase the delta t, because if we increase the delta t, we have less iterations, and so our model runs faster, okay? So we have a faster, a faster solution, or for the same time, we can have more cells, a higher resolution, okay? So this is always a compromise that we are doing. So we are always trying to increase the delta t as much as possible. But because in these two cases, both in the explicit and in the semi-implicit, some of the neighbors are from the old time step, we cannot increase the delta t that much, okay? So I'm showing you here an example. This was done with the model that we are using, the model that I will be using in the presential session. And you see this is the flow. The color is the velocity modulus, and the vectors are the velocities. In a bar, okay, of an estuary or whatever, a barrier island. So a tidal system, and the tide is going up with a certain velocity, and we have the maximum velocity here, okay? And these are the velocity modulus in a point somewhere here in the maximum, okay? During the ebb and during the flood, and during the ebb and during the flood, okay? So if the delta t is higher, so if the space between ti and ti plus 1, the time between ti and ti plus 1 is higher, the execution time decreases. So that's what I want, to increase delta t, to decrease the execution time. But if I do it, now I'm going to show you the results that way, you get this, you see? The velocity modulus start getting crazy in this point, and in a certain instant, it gets really crazy, okay? So we say the model instabilizes. And if you look at the map, it gets something like this, totally wrong. You see, it's totally wrong. And this chess pattern is very typical of a model that has instabilized, okay? So whenever you see this, you know your model is getting unstable, okay? And it's unstable because the delta, the neighbors in the old time step are too far away from the reality, okay? So this is a limitation of our model, okay? So we must always be trying to control the stability of the model, okay? And there is one non-dimensional number that controls the stability of the model, is the Courant number. The Courant number measures the space, so a velocity times a time is a space, right? Meters per second times seconds, you get meters. So this is the space that a particle of fluid moves in 1 delta t, okay? Compared with the size of the cell, okay? If the Courant is 1, so this is a non-dimensional number, it doesn't have units. If the Courant is 1, it means that in 1 delta t, the fluid will move 1 delta x, 1 cell, okay? If the Courant is 2, it means that in 1 delta t, the fluid will move 2 cells. And if it's 0.5, it will move just half of the size of 1 cell, okay? So, and this is a very important number to control the stability. So if you increase the current too much, your model gets unstable. Okay. Usually, the explicit models cannot have currents higher than 1. The limit is 1. In ADI models, in this alternate direction implicit, the current can go, our experience is that it depends on the system, the bathymetry, the forcing, lots of things, but we can aim of reaching 8 or sometimes 10, okay? It means it's 10 times faster than an explicit model. But even though we have this limitation, okay? So another model limitation. So for that, to show you this limitation, I would ask you to think about this hypothetical experiment, which is, imagine that you have a 1D model, like a channel, a river, a channel, something like that, okay? You don't have lateral variations, just in the main direction, okay? And imagine that you have a property, imagine a pollutant or temperature or whatever, that have this initial profile along, this is along the river, okay? Along the channel, okay? The initial property is like a triangle. So the concentration increases and then decreases, and the rest of the channel is free from that concentration, okay? And imagine that your model don't have diffusion, okay? I know in reality, we always have diffusion, but in the model, we can go there and we just nullify the diffusion term of the equations, and we get a model without diffusion, okay? So we can play with that in the model. So imagine we have a model without diffusion. What do you expect to have downstream? When this property moves downstream, you expect to have this, right? So the same concentration moves, but because we don't have diffusion, the triangle maintains, okay? So the model should do this, okay? A model that is correct should do this. But if you use a model, and this is the results I'm showing now, they are obtained with a model, they show something like this, okay? Like the one in red, these dots in red, you see? Although I have cutted the diffusion term in my model, the result resembles something with diffusion, okay? Which is strange. Why does this diffusion appears? Because I cut the term in my model, okay? And there are ways of solving this, I will show you later, you see? But you can never solve it completely, okay? This is a limitation of our models. It's called false diffusion, okay? If we have a model without any diffusion, due to numerical, I would not call it problems, due to the numerical nature of the model, we will always have some numerical diffusion. It resembles like the real diffusion, but it's due to numerical issues, okay? I will explain you very easily why does this happen, okay? So, yeah, imagine for the sake of simplicity that you have, imagine that you have the channel, okay? Instead of the triangle, you say that the concentration is 1 in the first cell and it's 0 in the rest of the channel, okay? And the velocity is from top to bottom, okay? So if the current is 1, okay, now you know what the current means, okay? The current is the space or the distance the fluid travels in 1 delta t compared with the size of the cell. If the current is 1, in 1 delta t, the fluid will move exactly 1 cell, okay? So in the next delta t, the fluid with the concentration of 1 will move from here to here, right? So it's 1 delta t, it moves 1 cell. In the next delta t, it will move another cell, and in the next another cell, and so on. So a long time, if the time moves, the position of the fluid with the concentration of 1 will be exactly in 1 cell further. Okay? So this is okay. But now imagine that you have the same situation, okay, but with a Courant of 0.5. So if the Courant is smaller, it will not instabilize. Remember, I told you the Courant is a number that will control stability. So if it's too high, it may get unstable and the solution gets crazy. But if it's smaller than 1, in this very simple model, if it is smaller than 1, it will not instabilize. But what does it happen? If the Courant is 0.5, in 1 delta t, the fluid will only move half a cell, right? So it will move from here to here, to half a cell, okay? But there are no half cells. You remember when I told you, when we discretize, it's not just putting a grid over a continuous space. It's not that. It's the space is no longer continuous. We just have cells. We have cell 1 and cell 2, and there is nothing in between, okay? So the best the model can do, this doesn't exist in the model. It's in our mind, it's easy to think about it, but in the model, it cannot be implemented. So what the model can do is this. Instead of 1 in halfway, it puts half to preserve the mass, to conserve the mass. It puts half of the concentration in each cell. So the total mass is conserved, but it distributes it to cells, okay? And then in this half will move half cell, this half will move half cell. So it will be 0.25, 0.25, and here 0.25, 0.25. The 225s gives half, and again, and again, and again. Okay, so what the model do is it resembles like a diffusion, you see? Although this term, so this model didn't have any diffusion. It was just the movement of the concentration along the channel, you see? So this is the reason why we have numerical diffusion. It's due to the incompatibility between the movement of the fluid and the space discretization of our cells, okay? And this is impossible to solve, okay? All models have this. The good thing is that usually, so the good thing is that in nature, we really have the real diffusion, okay? And usually the numerical diffusion is smaller than the real diffusion. So all the models will need to have diffusion because the real flow have diffusion. And we compensate the numerical diffusion during the calibration process, okay? When we are, one of the parameters that we use in the calibration process usually is the diffusion coefficient. And those diffusion coefficients, they are tuned using measurements, okay? And we tune them, and when we tune them, we are already taking into account the numerical diffusion. So usually there is no big problem with that. Usually, I said usually. In some cases, when we have very strong gradients, like for example, in the vertical direction in the ocean, when we have a very high stratification, or in an estuary, in a salt edge, in an estuary, where we have a very high stratification, in that case, it may be a problem. And then we need some ways of solving it. I'm going back one slide. I showed you here this quickest, you see this line, quickest is a numerical method that is more efficient in terms of controlling the numerical diffusion. So there are numerical ways of trying to control it. We never solve it, but sometimes we need to control it a bit better than usual. Okay, so this is another model limitation. Okay. returning to the question Fernando asked about the initial conditions, yes, these problems that we are discussing, they are, so the equations I show you, the Navier-Stokes equations, they are initial boundary condition equations. So it means that at the beginning, we need to give values in every cell. Okay, it's the initial condition. The value can be zero. Sometimes it's zero. For example, in a very dynamic system, in an estuary, the velocities can start with zero. And then we run 2 days of tide flow during 2 days for the model to adjust. And we know that during those first 2 days, the results are not okay. It's just a spinning up of the model for the values to adjust, okay? We can do that in an estuary. Start with zero velocities everywhere. In the ocean, no. If you were trying to start a model for the entire Atlantic with zero velocities everywhere, you would need to run it for, I don't know, more than 1 century to get real velocities. So it's not feasible to do that. In that case, what we do in very large systems, less dynamic, what we do is we start by using climatological averages, okay? We have climatological averages. We start from the climatological averages, and we also do a spin-up process in order to get the real results, okay? For that, we need to interpolate correctly the measurements and the climatological values. Usually the resolution is much smaller than our grid, okay? And we always need to do a model spin up. So you know that if you want to simulate day X, you should start day X minus something, depending on your system, in order for the model, when it arrives day X, you already trust the results, okay? And data assimilation, which is something that I will speak later, is also important to provide the initial conditions, okay? And then this is for the initial value, for the beginning of the simulation. And then in every time step, we need to supply boundary conditions, okay? And when we say boundary conditions, I'm talking about the lateral boundary, so the part of the system that is outside my grid. I must impose what is happening outside my grid at my lateral boundary, okay? But also in the bottom, so the condition in the bottom, usually it's stress in a physical model, but if you have a ecological model, can be fluxes of oxygen, of nutrients. So if you have a sediment model, can be fluxes of sediments, whatever, in the bottom, okay? And in the surface also. In a physical model, the surface can be stress due to the wind, or some Stokes stress due to waves. But in another model, in an ecological model, in a primary production model, can be fluxes of oxygen or light or temperature or whatever, okay? Also, we sometimes use sponge layers. So usually the results of the model close to the boundary are always bad, okay? So we should place our boundaries far away from our place of interest. So in this case, if you are interested in this estuary or this coastal area over here, you cannot place your boundary here. You should place your boundary far away, because you know, close to the boundary, the results of the model will always be wrong, okay? So avoid putting the boundary close to your region of interest. And sometimes we use these sponge layers, which are some stripes around the boundary where we have very high coefficients of diffusion to stabilize the imposed boundary, okay? And also radiation conditions. I will not talk too much about that, just to say that the radiation conditions are, it's not solar radiation, it's the radiation of waves from the model to the outside. Okay, so sometimes we need to have a boundary condition that allows the high frequency waves created inside the model to radiate outside, to be lost to the outside of the model, in order not to compromise our solution. Okay, so this is very rapid. Boundary and initial, especially boundary conditions, is a science on itself. So I won't take too much time on that. Okay, so now let's move a bit to downscaling. So downscaling. So let me talk about a little bit about operational modeling and downscaling. So basically, I won't get too much on this. We will have other classes talking about this. So basically, we have different observations of the ocean using different platforms and different systems. I'm showing here the EuroGoose, and all these observations are supplied to a model. In this case, I'm showing here the Copernicus marine system. It's a global model or a global set of models. And with those models, we can have products for different applications, okay? You will talk about this in other classes, or maybe you already talk about this. The thing is, these are global models. They address the entire globe. So the resolution is not as high as needed for our coastal activities. So there is a way of using these models to create models with higher resolution, and that process is called downscaling, okay? In the downscaling process, what you do is you use the global models and observations to supply the initial and boundary conditions to your local model with a high resolution, okay? And then you use that local model to give products that are more useful to the communities around the coast, okay? So this is the basics, the idea, the concept on downscaling, okay? I'm just showing you very briefly two different cases that we are running at the University of Algarve. One is the SOMA system. The SOMA system is the operational model of the coast of Algarve, or the South Iberia coast, if you want, because it has a little bit of Spain also. And this one is the basic system. It is being run in Cartagena Bay in Colombia. So there are two different concepts, two different applications of the same concept, okay? And they are being driven by the global models. So when we say it's operational, it means that every day we are running the model and producing results for the next 3 or 4 days. So we are doing forecast, okay? So we are predicting the future. Okay, so very briefly, different types of models. We have different finite differences and finite volumes, okay? The big difference between them is that they both use these Cartesian orthogonal grids. Big difference is that the finite difference, we transform the differential equations into algebraic differences, okay? While in the finite volumes, we transform not the differential equation, but the control volume equation into algebraic equations. The big problem of finite differences is that they are not conservative by nature, so we have conservative problems. So it means the properties do not follow the conservation law, okay? And it's also difficult to implement curvilinear meshes. While in the finite volumes, the conservative property is assured by nature of the model, and the curvilinear is very easy to implement, okay? But finite differences are very easy to teach, so they are still being used, at least for teaching. Okay, and then we have finite volumes, finite elements, and finite elements is a different class of models. Usually they use the triangular mesh, but the differential equations, they are transformed into sets of form functions, which are adjusted to the solution, solving a minimization problem, okay? But they have conservative problems, and it's difficult to include the convective term, as I said. So usually they are not very popular in fluids. The big strength is that it's easy to implement an unstructured mesh, but the finite volumes is also possible to implement in an unstructured mesh. So, well, anyway, these are the different methods that are popular. There are others, but these are the most important. Okay, so basically all these methods, what they do is they solve the transport equation. Again, it's here. So this is the two terms of the temporal variation and the advective variation. This is the diffusion term, and then sources and sinks. When it's the Newton equation, so the Navier-Stokes equation, the sources and sinks are forces. But in the case of water quality, for example, the properties are the concentrations of phytoplankton, zooplankton, and so on. And the sources and sinks are the processes that transform one property to the other. And usually it's like this. So imagine you have all these properties which are being solved, being transported in our domain, and all these arrows here, so they represent the sources and sinks of each property. For example, for nitrate, the nitrification is a source, and the nitrification is a sink. Okay, for zooplankton, phytoplankton is a source, so because zooplankton eats phytoplankton, and higher trophic levels is a sink. Okay, you see, and all these connections are done in the source and sink terms of the equations. Okay, see, this is the way of implementing the water quality. For example, if you have a sediment transport model, the property, the alpha, will be the sediment concentration, which is being transported in the water, okay? So you have advection, you have the temporal variation, the advective variation, the diffusion of the sediments in the water, and then you have sources and sinks of sediments in this case, and the sources can be the erosion of the bottom, the resuspension, and the sinks are the sinking, the deposition, okay? And then you have flocculation, compactation, whatever in the sediment, okay? So this is another way of applying this generic methodology, in this case for sediment transport, okay? For energy, for water temperature, okay? In that case, the alpha will be the temperature, so it's being transported in my water column, and the sources and sinks are solar radiation, sensible heat loss, latent heat loss, light attenuation, stratification. Okay, it's all those processes connected. Okay, so you see that this is the common structure. It can be applied for the hydrodynamics. In that case, the alpha will be the velocity. For the water properties, for the sediment transport, to the temperature, also to the salinity. It's not here, but the salinity would be something similar. Sources and sinks would be different, of course, but it's the same logic. Okay? And when we have an operational model, we need to run the model every day, as I told you. So I'm showing here a possible cycle, is the cycle that we use in those two operational models that I've shown you. So basically what we do here is, so every day the model runs. During the morning, for example, during the first hours in the morning, it runs and it produces a simulation for the next 4 days, okay? then in the next day, we pick the results, and it's being forced, you know. So all this simulation was run during the morning of day one. So to run it, we need the boundary conditions of the future situations. That's why we use, so this is a downscaling approach. So we use the forecast of the global model. In this case, it's CMEMS. We use the forecast of CMEMS to run this model, okay? And then in day two, we restart the model. CMEMS already have new boundary conditions, so we are going to run again the same days and plus 1 day. And then again and again and again, okay? But once in a while, although we are supplying boundary conditions that are being updated, so, and CMEMS, I will go later how, well, CMEMS don't have a global model to do it. So I will go later explaining how CMEMS do to be able to run in the future, okay? Even though in this downscaling approach, although we supply boundary conditions every day for the future, the results start diverging from the reality. So after a few days, we need to make a home set of the reality. So we should restart the model again with the initial conditions that are closer to the reality. For that, during this day 7 or starting day 6, we do, it's not okay, this is not correct, this just takes 1 day to be done. We start a new cold start and hot start with new initial conditions, okay? And then we have new initial conditions to give to our downscaling model. So, and we start this cycle once again. You see, this is how we are running up our operational model. This is one method. There are other methods I will explain you later, namely the Copernicus. It doesn't have a global model to get boundary conditions from, so he must always be being updated with the measurements of the reality. And I will show you how it's done. So this is just a schematics, a fluxogram of the different processes that we need to do during an operational cycle. Okay, so we need to process data, produce the simulation, control the simulation to see if it's automatically control it to see if it's going okay, creating reports of success, of failure, and then store the data in databases. Those databases that then can be used to supply data for the interface that I show you, okay? And even for people to download the results if they want. By the way, those two models are open, so everyone can download data for free, okay? Okay, so I kept in the air, how do CMEMS do it? Because CMEMS cannot be supported by a global model to run it. So it uses a methodology called data assimilation, okay? And that's the same methodology that is used to produce reanalysis. And you probably already heard about that name, reanalysis, and there are a few products in CMEMS of reanalysis of data. So I will try to explain very briefly what does it mean, reanalysis. So the data assimilation is a process that combines results from models and measurements into a new product. And it recognizes that models have errors, okay? So as I told you, models are not right, they have errors. And we must know how much is the error of the model. We must have an idea of the error of the model statistically, how much is the error of the model. And it also uses observations, but it also, this methodology also recognizes the observations have errors. Okay, so obviously, just one person that never went to the ocean to do a measurement may think an observation is perfect. An observation is not perfect. We have errors of the sensor, errors of the platform, errors of methodology, so many types of errors, okay? So, and we must also be able to quantify the errors of the observations, okay? And it picks these two data sets, okay? The data set of observations, which has very few observations, and the data set of the model that has a lot of model results, and it combines the two into something that is closer to the reality, taking into account the errors of the observations and the errors of the model, okay? So given this as a very, very rough idea. So this picture may help you explaining a bit more what it means. So imagine that you are God and you know the truth, okay? The truth would be this line, okay? In a certain variable, it would be this line. No one knows the truth, okay? What we know, if you do observations, you get this value, okay? It's close to the truth, but it's not the truth. And you have this error around the observation, okay? So you never know how much is it the truth. And then this is your model. Okay? Your model gives this value, and this is the error of your model. Okay? So, and you want to restart your model. Okay? If you were God, you would restart it in this point, in the blue line. Okay? But we are not God, so we don't know this. So, and it doesn't make sense restarting the model in the observation, because we also know the observation is wrong. It has some error. So we should come up with some point to restart our model that would be halfway between the original model and the observation. It should minimize, in terms mathematically speaking, it should minimize the error between the new start and the model and the new start and the observation, okay? So, and this is done using data assimilation, okay? This is just one point, but remember that you have 10 million cells here in the model, and you have 10,000 observations here, coming from satellite data, gliders, Argo buoys, whatever. You see? So you have a certain number of observations, many millions of points in your model, and you should be able to, in a mathematical process, to get this new state of the variables in your model, the new restart, the new initial conditions of your model, okay? And then you run again one more period. It doesn't matter if it's 1 day, 1 week, or 12 hours. So it's your period between assimilations, okay? And again, you do new observations and you run the same process. You restart your model and you run one more period, okay? So this is how data assimilation is used, and this is how Copernicus does in the entire globe to restart the model and to be always as close to the reality, to what we think it's the reality, not closer to the observations, but closer to the reality, okay? So the observations is this. We are not trying to get closer to the observations. We are trying to get closer to this blue line that only God knows, okay? So this is a very simple way of explaining what data assimilation is. There are many types of data assimilation. The one that I was explaining is this, the sequential intermittent assimilation. So you have a running period, an analysis. So this process that I was explaining is called analysis. one analysis, then you run the model again, then another analysis, you run the model again, and so on and so on, okay? There is also sequential continuous assimilation. While you don't stop the model, you manage to input and change the model while it is running, okay? And there is the non-sequential intermittent assimilation, okay, which is you are changing the model along its movement, along its computation, and then suddenly it's too far away, and then you restart the model and you run it again and again, okay? And there is also the non-sequential continuous assimilation, which the model is just running one continuous time and the observations is being included, okay? So there are many types of assimilation. Okay, when we talk about reanalysis, it's similar to this, but the reanalysis is done afterwards. Okay, so some of the observations that are done, they don't arrive on time to be included in the model. They arrive later, so they cannot be included in the operational model. But at the end of a period, let's say every 6 months, we can pick all the model results and all the observations, both the observations that were used to run the model, plus the observations that were not ready at that time, but that now we have ready. And then we can run this process again, okay? Pick the model results, all the observations available, and we run the model again, and we get, with these additional observations, okay, we get the reanalysis, okay? The reanalysis, it's different from the forecast. And you may think, okay, so maybe the reanalysis, if I'm not looking at forecasts, I want to do something with hintcast or nowcast. Nowcast, no, but hintcast. Maybe it's better to use the reanalysis. The thing is that running this process again will produce something that on average is closer to the reality, on average, but the solution gets smoother, you see? So the big gradients disappear. So it's a drawback on that. So if you are looking at the big picture, it's better to use reanalysis. But if you are interested in big gradients, like the plume of an estuary coming to the coastal zone, a reanalysis will probably blur all the gradients and your plume will be kind of blurred, you see? So there are pros and cons of using reanalysis data. Anyway, this is what it is. And I'm almost ending, so I guess I will manage to do it in 1.5 hours almost. So the final thing is talking a bit about model calibration and validation. So after we do all this stuff, having a model running and producing results, maybe we are very happy with it. Whenever we look at model results, they look very beautiful. You can do very beautiful plots with lots of colors and it really resembles reality. But you cannot use it yet, okay? You cannot use the model results, even if they are beautiful, if you don't calibrate the model, okay? So when you calibrate the model, what you do is you run the model. So you have a set of observations and you run the model many times, tuning the parameters of the model, tuning the horizontal diffusion of the model, tuning the bottom stress coefficient in the model, tuning, I don't know, the assimilation constant in phytoplankton, whatever, okay? It depends on the model. Usually what we do is first, before we calibrate, we do a sensibility analysis from all the the parameters of the model, we try to identify those that produces more changes in the model, those that the model are more sensitive to. And then we run many times the same problem, tuning the parameters with different sets of parameters and trying to see which set of parameters give the best results, comparing it with the measurements and see which gives the best results, okay? And then, so this is stage 4, is the calibration, okay? And it is compared, so the model is compared with the calibration data set. And when we are happy, so we do this many times, okay? Until we are happy with the set of coefficients. But we may think, okay, the model is running okay for this situation, for this particular situation of this data that we have. For example, in a estuarine model, for example, the spring tide of a certain day, we got these measurements and the model is running okay. But what is my guarantee that the model will also perform well in neap tide? Yeah, so we are calibrating using spring tide. So then after we calibrate the model with a set of parameters that we encountered, that we identified, we should run the model with a different situation, with a different set of parameters. For example, this is spring tide, this should be neap tide, or whatever. This is winter period in the coastal zone, this is summer period in the coastal zone. So they must be independent data sets. And the model with the same parameters that we identified here should also perform well. So it should compare well with the data, with the observations for this other period, okay? So this is called validation. So after calibration, we should do validation, and only after these 2 stages, the model is okay to be used, okay? So this is very, very important. And whenever I say, okay, I compare the model with data, the question is, how do I compare model with data? What do I compute? Is it the error? If it was just 1 point, you see, I would say, okay, it's the error. I have 1 value of the model variable, 1 value of the observation, and I compute the error. It can be the absolute error or the relative error. Usually the relative error is better, but it's just 1 point. The thing is, the model may be 10 million points. Okay, so we have 10 million cells in a model, it will have 10 million points. And we have 100 or 1,000 observations. How do we compute it over time? How do we compute it? How do we compare it? So there are different ways of comparing. There are different metrics and there is no recipe. We should use our good judgment and all the tools that we have on hand. So root mean square error is a possibility, okay? If it is a time series, usually we use root mean square error, or it can be of a certain point or of the average of the values of the domain or whatever, or the surface or whatever, okay? So sometimes we try to interpolate the points. We must be cautious with that. So this is the fitting of the data, okay? But this is overfitting. Naturally, the nature don't behave like this. This is just this dispersion of errors in the observations. And we should not try to have our model doing this because this is error of the observations. We should have our model doing this, okay? Also, sometimes when we have waves, for example, in tides or in velocities of a tidal system or whatever, sometimes the error is not in the value, but in the phase. So we should decompose both the observations and the model results in the frequency domain and compare. So basically, we should do, for example, a tidal component.
Looks like we lost Flavio. I'm trying to contact him.
Hello.
Okay, we see you again.
Yeah. How much did you lost?
Not much, maybe 3 minutes.
So I was speaking just for myself during 3 minutes, is
Yeah.
it? Oh my God. So let me see. Let me share this again. Do you remember the slide I was in? Was it this or this?
No, for this.
This?
Yes.
Okay. So I will restart from this.
You are talking about the phase
Yeah.
difference.
Okay. So it was not that much. Okay. So I guess I will share the presentation mode. Yeah, basically I was just commenting that sometimes we should compare. Sometimes the error is not in the value itself, it's in the phase. So when we have processes that have a wave behavior, sometimes it's a good idea, like for example, the tidal processes, sometimes it's a good idea of decomposing the values, both the model values and the measurements into components, like we are doing here. So we have measurements from a tide gauge, and we decompose and into components and constituents, and we do the same with the model results. We decompose the model into constituents in the same points, and then we can evaluate amplitude errors and phase errors. So it's another possibility. So as I said, there is no recipe. Each case is a case, and we should use. Another way interesting when we do this is to compute the power of each, the energy of each component. And we can see if the model is producing the right energy at the same frequencies of the nature. For example, in a tidal system, the highest energy in this case is M2, is the frequency of the M2 constituent. And if the model produces the same energy or similar energy, it's a good bulk sign that the model is performing well. Okay, so I'm just finishing with all the issues the topics that I've been discussing with you. What is a model? So we saw it's an approximate representation of reality. We saw the two formulations to transport a property, okay, which are equivalent. They produce different model types, the Eulerian models and the Lagrangian models. we saw discretization in space and time. Okay, so we saw different types of meshes and also in time, what is explicit, implicit, ADI, and so on. So we talk about some model limitations. We saw the Cura number, how it controlled instability, and also how it controls numerical diffusion. And we saw initial and boundary conditions. We saw they were necessary, they produce errors, and they influence the results. We saw how downscaling is done, okay, to produce models with higher resolution using boundaries from global circulation models. We saw different types of models, okay, numerical methods, the variables that are computed. And we saw how an operational model works. It runs every day. It restarts from analysis of data for initial conditions. We saw a bit of data assimilation. So it combines model and observation to produce analysis and also for reanalysis. And finally, we talk about model calibration and validation. We saw it is necessary and that there are many ways of comparing data. And this is it. I don't know, any question, please, you're welcome. You can use these minutes to ask something.
Could you recommend any reading or maybe like freely available online lectures about the finite volumes models? Because I'm not super familiar with it.
Okay, finite. I would say a good reading is the I can put it here in a way. Malasakera. I don't know if I'm pronouncing the name correctly, but I will put the reference in the chat.